Hi, my name is Alvaro Agea and my partner is Daniel Higuero. And we are happy to be here to introduce a technology we have been working on for the last month. We call it Stratio META. And the basic idea is to provide a distributed data hub that is able to integrate streaming and batch queries. Even though the internal name of the project is Meta, we have made a little change, and it has been renamed Crossdata. No? Okay. Okay. You know the marketing people, and I need to change the names for the products. And you will find both names coexisting in the near future until the first Crossdata release is launched. Before we begin, we would like to present Stratio. Stratio is a big data company formed in 2013 that currently has over 50 employees in its Madrid office. Our technical team is currently located in Spain, but we have a local office in San Francisco. We focus on offering a big data platform based on the Spark ecosystem, and we have been recently become and certified Spark distribution. It's so obvious that we like Cassandra. It offers many factors that are attractive for big data application. Especially its peer-to-peer architecture, its fabulous read-write performance, its fault tolerance implementation, and its easy of use, among others. Once we have to introduce ourselves, let's focus on the talk. We're going to overview the motivation behind Crossdata. Next, we're going to describe its architecture and how metadata is managed in the system. After that, we will show you the integration with streaming sources and our custom secondary indices built over Lucine. Then we are going to briefly describe our integration with the Spark and ODBC connector. Finally, we will talk about our futures ideas. When we think about big data analysis, usually the first thing that comes to our minds involves batch data. However, each day we see more users introducing streaming sources at some point of their architecture. In those cases, they tend to rely on composite architectures involving several products. Not only that, but when we talk about big data platforms, users face the problem of how they start using them. You have the system installed, but it's difficult to start using it. Several methods to launch jobs, several types of queries, many specific languages. For example, Datastore Enterprise have 3 different methods to access the Cassandra data. So we need to find a solution for those users. If we try to list the main requirements, we find the following: easy deployment and administration, nice write performance, and an easy language. These features are already provided by Cassandra, but others are not. Integration with business intelligence tools, which usually means the ability to make joint queries, support to streaming sources, integration with other databases, and query flexibility from the point of buy of the underlying schema. Users want to query our data, and sometimes the queries cannot be done just because we have a schema limitation. It is in these points where Stratio Crossdata can improve our big data system. Crossdata is a new technology that has been in development for the last month. It is current open source with Apache license, and it has several new features that we think will change the iteration approach with big data system. Crossdata avoids the limitation imposed by underlying datastore. For instance, if a column has not been indexed, we need to think about methods of retrieving that columns. It is important to highlight that our focus is on users and performance. If the user requests some data, it is important to provide that results. We think it's better to answer a no-optimal query in the system that provides it. We will always have time to add a new index if that query becomes in the norm. As an example, think about users not involved in the database design that interact with the system through business intelligence tools. For this reason, we use Spark to perform non-natively queries in those cases. And we also use it when we need to mix data coming from streaming sources with batch data. Moreover, our designs allows us to access several clusters and technologies at the same time. From the architectural point of view, we can define the three main layers. On the top, we find the driver, which is used to build custom application through his Java API. We have also ODBC connector for standard tools, and we provide REST API. On the middle, we have our server component, which contains the core logics and the distributed capabilities. On the bottom, begin and generating architecture, we employ a connector-based approach that permits to extend the system to communicate with any data store. Communication between layers is accomplished using a Scala actor framework. With respect to the connector approach, we have defined Java interface that contains the set of operations that an ideal connector should provide. Notice that our design simplifies connector development so users can easily add their data store to the Crossdata ecosystem. Each developer will define which are the connector capabilities, and Crossdata, with its planner, will choose the best one depending on the query. Several connectors to the same data store can coexist at the same time. To clarify this, our query execution path is pretty similar to the existing ones, with the addition of the connector selection step after the query planning is determined. Another nice feature is related to multi-cluster support. Many times we have seen an application that has two completely different types of accesses. Will it be nice if we can easily tune its database? If both types of accesses target the same cluster, this is usually impossible, as you need to decide, for instance, if your workload is write or read-oriented. With Crossdata, a common logical view is provided to the user independently of which is the cluster storing a particular table. We only have imposed the limitation that a table name can only be found in a single cluster. To illustrate this, let us imagine a scenario with three clusters: one production Cassandra cluster, one developer cluster, another cluster with an old version of the database or other technologies. In this case, if we submit the following query, Crossdata will determine which is the data store persisting table users, and it will retrieve a result set without requiring any knowledge from the user point of view of physical deployment. Now, let's focus on metadata, and how we can solve its management problem when we have different technologies. The first question that arises when we talk about metadata is who are going to be compatible with its schemaless approach. It is true that some data stores are schemaless, but it is also true that our application need to know what fields should be queried and so on to the user. The difference for us is not whether a data store is schemaless. It's more related with providing the user with a flexible way of updating existing schemas. Crossdata stores schemas for any data source, independently of whether they are schemaless. Remember that sometimes other applications like business intelligence tools do exist, and they require schemas. To show how it's done, even though in Cassandra, we already have a schema. So for that, Crossdata store and shares the schema itself among the existing Crossdata servers. This is also important to reduce the metadata related queries to the underlying stores. For instance, during the query validation. Next in line are streaming sources. These days, we see more projects that require or involve some level of streaming sources from Twitter to alarm events, fraud detection system, etc. In order to be able to manage streaming sources within Crossdata, we have defined a new concept called ephemeral table. Given that the streaming sources are themselves ephemeral in nature, even come in the system, they are processed and they disappear of the system. Ephemeral table seems like a nice way of treating this type of data. An ephemeral table is an abstraction that allows us to work with streaming sources like typical bash table by means of define the entity and their schema. When we have a streaming data that has the same information of a batch table, we need to think about who to query it. Streaming queries are infinite by definition. We have an incoming stream of data that we don't know when it will stop. Streaming queries therefore need to specify which is the time window used to retrieve a set of data to be processed. This also means that a system that supports streaming queries should provide a method to list running queries and to stop them. As an example of our systems, we use the classical select syntax with the addition of the window clause. The window can either be given in amount of time to wait or in absolute number of tuples to be retrieved. Additionally, it is important to highlight the complexity of the query affected by the system. It's not limited by the fact that the stream of data is involved. We are proud to announce that we support joint operation mixing batch and streaming sources. For example, in fraud detection scenario, it will give us the possibility of analyzing whether a string of transactions contains a blacklisted credit card, only in one query. In summary, we are able to treat streaming data as batch and can therefore execute the same time of queries on it. Now, my partner, Daniel Higuero, continues to use more features for Stratio Crossdata.
So, other important feature of Crossdata and the relationship between Stratio and Cassandra is the support we have added with filter searches on Cassandra. The filter searches are solved using a Lucine integration. It's our custom Lucine integration, and it provides the user with filter support. This integration is not limited to only filter support, but you obtain all the nice features of Lucine by default. So you can employ basically all the Lucine syntax to query the data, the columns that are stored in Cassandra. If you're interested in the code, you can check it out from the GitHub URL that you see on the bottom of the slide. To see basically how it's done, what we do is just, we have the ring of Cassandra nodes, and we add a local Lucine index per node. That index only stores information about the columns that are stored in that particular node. When a query arrives to the coordinator node, what happens basically is that the query is distributed as it is typically done in Cassandra, and we retrieve the results from that particular index, and then we have a special map reuse type of logic just to merge all the results in the coordinator node and return the results to the user. With respect to the syntax we use in Crossdata, we have made a slightly change to the creation and the query syntax to easy the use from the point of view of the user. You have tried sometimes or any time to create a custom index in Cassandra, you will find that you need to basically create custom index, and then you need to pass a lot of options to the index, specifying which is the class that is going to be executed, and a lot of options of your particular implementation. With this, you can just write, I want to create a full text search, a full text index in that particular table. And another important part is that with our indexes, we can index several columns, and that information is maintained only in a single index. So there is no need to maintain several secondary indexes per table. In just one, you can index all the data that independently of which is the type or the analyzer that you want to use for that particular column. With respect to the query syntax, what we have done is to add a new operator called match, and that operator exists basically to tell the user that the thing you want to match, in this case the email, you want to find all the emails that belong to that particular domain and not just the star@stratio.com. So it is important from the point of view of the user to understand that whenever you are going to write a match operator, you will use Lucine syntax and not the typical one that you will get if you write an equal instead of a match. Next, I want to talk about our integration with Spark and how we connect Spark to retrieve data from Cassandra. For those of you who are not familiar with this technology, Spark is a distributed framework that implements kind of a MapReduce logic, but it performs things differently from the classical Hadoop approach. In particular, it's focused on in-memory processing, and it's everything around the concept of RDD. And RDD is just a specification of what are going to be the set of transformations that need to be applied to an input data. It offers a simpler API that you will get with Hadoop, and it also increases the flexibility you have to write the set of transformation. So we can now forget about those identity mappings, identity reduce that you need to put in Hadoop just because you want to perform a set of iterative reduce steps. Another important thing that happens right now after the announcement of Spark SQL is which is the difference between Crossdata and Spark SQL. From our point of view, we see it as we have a different approach to query execution. We only use Spark whenever the native driver doesn't support the query we want to make, because we believe that native drivers are faster for obtaining several rows. So if the functionality we want to obtain is already implemented natively, we will use that driver. If what we want to do is, for instance, perform a join query, then I cannot use the driver in Cassandra because it's not supported by Cassandra, so I will do it in Spark. Additionally, with this type of approach, we are able to overcome some existing limitation in Spark, like the problem you have when you want to manage several batch and streaming contexts in just one Java virtual machine. So to illustrate that, on the left you have basically the Spark SQL approach, which is I write a query, I say this is Spark SQL, and then I will launch a Spark job. You will get the context, you will get your data, and you will get the final result to the user. With our approach, what we do is we write the query, we analyze it, and we determine whether that query can be basically solved by the native driver, or you need any other thing to solve that query. So the important part here is to determine whether you will go through the native driver or you are required to make a Spark approach with the overhead that is involved in that decision. About our Cassandra Spark integration, this is something that may sound new, but we have started that project in 2013. Our objective was to provide a method to retrieve data from Cassandra from Spark. And we make our initial approach based on the Hadoop input format interface, but we have now, after some benchmark, decided that it is better to, even in that particular case of using Spark, go through the native driver of data stacks because you will get results faster. If you want to check out our integration with Spark, you can just download the code from our GitHub URL. About the differences between the dataset driver and ours, we are in the process of publishing a benchmark comparing both approaches. And right now, what I can tell you is that the results are highly influenced by which is the split size you use, which is basically which is the amount of rows you will get at once. And we are seeing some good results that are promising for our implementation, obtaining for the group by up to 40% faster results than if you use dataset driver, and joins can be performed up to 17% faster with our implementation. So I will advise you to stay tuned for the benchmark publications so you can compare both solutions. Another thing that I find interesting is sometimes when we compare which is the approach we have. We can either create secondary indexes for accessing our data, or we can just go through Spark. We have made also some benchmark with it, and what we see is that it highly depends on which is the amount of rows that will be stored in your index. There is some point in time that it will be better to go through Spark, but there is also a large portion of the time that it will be better just going through the Lucine indexes in this case. And finally, it's time for the ODBC. ODBC may sound like an old technology, but it is currently used in many, many places. So we have developed an ODBC driver that is able to retrieve data from Crossdata. And that allows us to integrate with different applications and internal tools. In particular, we are focusing on offering a solution for those users that have already bought some business intelligence tools that may be Tableau, ClickView, or any other. And you get a big data platform, but some part of your working environment is not going to be affected. And you should maintain backward compatibility to that part of the business. So with our ODBC, you open the possibility to retrieve data for any data store that can connect to Crossdata, and you get just one ODBC that will get data from many sources, independently of which is the technology, which is the cluster, or where are you going to store your table. About the future research lines of our product, just to mention a few, we plan to focus on the security implementation, on adding a security layer that will be able to allow you to control unauthorized users. We are going to work on Query Optimizer and a smarter query planner. This is something that you can always work on it, so we are planning to improve it. We will leverage some system statistics. I cannot tell you how right now, because there is something for another talk. And we are also planning to support user-defined functions. There are many users that already have defined user-defined function for the data stores, and it will be nice if we can support them so they have also backward compatibility with the system work they have done. And one important thing is that we would like to become an Apache project. We have an Apache license, and we would like to become an Apache project. The URL for the project is on GitHub, so you can check out our effort on this Crossdata project. And we would like to ask you for help, because if you want to become an Apache project, you need to follow some rules from the Apache Foundation. And the first one is trying to find a champion. So if somebody of you want to help us or know anybody that can help us, we will be glad to hear from you at any point in time. And well, we'll try every day to contribute to Cassandra, in particular with our Lucine indexes. We also have made some wish list, let's say, for Cassandra, based on what we have seen from the code, what we see in our brainstorming sessions, and we would like to offer this as a possibility for any other people to take from it. First, if we imagine a big data system, there is the possibility that somebody launch a query that may kill the cluster at some point. It's not well designed, something happened, so it will be nice if we have a method to kill that query. So it's going to be something like going to the coordinator and saying, okay, stop it, but there is no method right now to stop queries. With respect with integration our indexes within Cassandra, we have seen some problems with respect to how exceptions are managed. In particular, there are some paths that are not clear, and you cannot follow an exception path if you have an error in your particular custom index. And finally, we have seen another point that will be able to improve the Cassandra performance, and this is based on which is the work that is done in the coordinator. There are some functions, like we perform a count of all rows, that could be highly, that could be nicely implemented if we just run that particular count to the different nodes that are involved in that query, and the coordinator will only coordinate that result and merge the result instead of counting them. So that is something that could be added to Cassandra. We think that it will be faster for many queries that we are seeing every day. So with this, we finish our talk. So if you have any question right now or after the talk, we will be happy to answer. I don't know if the mic is going.
Hi.
Hey.
Can you tell me what size data cluster you've done with the full text indexes?
Sorry?
What size cluster, how much data have you done with the full text indexes?
I can right now give you the numbers, but they will be published in the benchmark. There are, right now the benchmark is just a few nodes, let's say more or less 10 nodes, and there will be enough data to compare the solution.
So how does your solution with Lucine based indexing compare to solutions out there like Elasticsearch and stuff like that?
I'm afraid that is in the same answer that the other partner. I don't have the results right now. They will be published in the benchmark.
Right. So I was asking feature-wise.
Feature-wise is you get everything that Lucines give you. So you get all the features. All of them are exposed through our interface. So you can either solve match queries. You will be able to solve, if not now, in the future, range queries, fuzzy queries. Everything will be offered to the user that is on Lucine.
Yes.
If not, you can always use the other syntax that right now, the syntax that you use, you don't have this match operator. We support other syntax that is not that nicer, but it works for the application.
So does it support like the full range of Lucine APIs or?
Yeah.
Okay.
It's supported, not more nicely or not, but it's supported.
Thank you.
You're welcome.
When you are using the secondary indexes, how much faster could that be compared to the data stacks integration between Spark and Cassandra?
The use of secondary indexes, it can be also used when you use Spark. When you want to retrieve data from Cassandra, you can also decide whether that particular query made inside the Spark goes through the Lucine indexes, and it's quite faster. I mean, you will get more than 10 times faster than if you go just without the index. Okay, thank you.
Thank you very much.